although I cannot see you now because I'm in a full screen mode, so I can only see my slides, not everyone. But if you have questions, do not hesitate to raise your hand, and Marco will tell me that I have to stop. Okay, so yeah, so as Marco mentioned, I'm now a postdoc in condensed matter theory group in UC Berkeley. During the last few years as a postdoc, I've worked on various aspects of quantum dynamics, including operator growth and thermalization, broken integrable systems, open quantum dynamics. Whereas in this talk, I will focus on a recent work which is related to realizing so-called scramblers, so very chaotic quantum systems. Yeah, so as the title suggested, the talk will be concerning a new type of Sachdev-Ye-Kitaev model. So it will be nice to introduce the classic Sachdev-Ye-Kitaev model, which has been attracted a lot of interest since a few years now. So this model is a quantum mechanics model in 0 dimension of a large number n of fermions. So in this case, I've written Majorana fermions gamma I, and they interact via a O2O by O2O interaction matrix, which is completely random and independent and full. So in a large n limit where you have a lot of fermions interacting, this model is exactly solvable by the so-called dynamical mean field theory, or Schringer-Dyson equation. Basically, the action becomes classical. And what's remarkable also about this theory is that if you go to low temperature, if you go to 0 temperature, you will see that it realizes a non-Fermi liquid. So its excitations are not described by quasi-particles. And another remarkable feature of it is that it realizes so-called maximal scrambling. So if you compute its out of time order correlator and the Lyapunov exponents, you will see that it's the maximal value according to the bound of Madachenda, Stanford, and Schenker. And that suggests that it's a kind of holographic matter. So it's a quantum system. It's a quantum system in 0D that is dual to a classical gravity system in 1D. Okay, so this is yeah. Is there a question?
No, I think we're good.
Okay, very good. Okay, very good. So these are the theoretical merits of this model. I think they are by now quite familiar. So many groups of experiments and theorists are trying to realize this model in various settings, so that we can for example study holography and gravity on a tabletop. However, this turns out to be hard. So the obvious reason or the superficial reason of this is that you need to assemble a large number of fermionic degree of freedom and let them all interact without any spatial structure. But actually, there's a more fundamental reason, which is in a renormalization group sense. So it's really it can be summarized as the fragility of SYK. So actually, if you look at the Hamiltonian on top of this slide now, it has a SYK2 term, SYK4 term, so 4 Fermi interaction. But I also added the so-called SYK2 term. It's a two-body interaction, and usually this two-body interaction will be there in a realistic system because you always have some tunneling. And in the RG sense, this term is relevant. So whenever you have this term, whenever you cannot suppress this term completely at low temperature, it will dominate, and you you will get back a more boring Fermi liquid at low temperature, and you won't have this maximal scrambling that gives rise to holography. So you lose all the interesting features. So then a very interesting question is how do we avoid this and realize true SYK low energy state? So now I will start to review a few experimental proposals by other groups and also by our collaborators to do this. So the first proposal is the following. So as you can see, it's a paper that is written in 2018 by a group led by Marcel Franz, and their idea is to use the so-called graphene flakes. So a graphene flake is a irregular piece of two-dimensional graphene. So as you can see in the picture. So now how does this work? The crucial thing is that you need to add a transverse magnetic field into this material. So you need to inject a magnetic flux, and when you do that, as their calculation shows, you will the single particle modes of this graphene with magnetic flux will have a highly degenerate so-called the lowest Landau level LL0. So in this plot, which I took from their paper, you can the y-axis is the energy of single particle modes, and the x-axis is the magnetic flux. As you see, if I increase the magnetic flux, I will have more and more single particle modes quenched in at energy 0, and that is protected by some Carroll symmetry, and you have so many lowest Landau levels. So what is great about this is that now you can project action 0 onto LL0. Now on LL0 you don't have any dispersion, so you don't have two-body term. Now you can write the projected Hamiltonian as the SYK form. It's a complex SYK, but the physics is similar. So you have JIJKL described by a complicated matrix given by the Coulomb interaction projected to a lowest Landau level. Okay, so in this paper they claimed that this is a way to realize the SYK interaction. So indeed, they solved the problem of a two-body interaction by quenching to LL0. But however, is this JIJKL tensor, so this huge tensor of interactions, really featureless as in SYK? So actually, it is not, and it is not very hard to show that if you view JIJKL as a matrix. So if you group IJ and the KL as group indexes, then this matrix has a low rank structure. So actually, you can show that its rank, which I denote as R, is proportional to the volume, so N, the number of fermionic modes. Whereas the maximal rank, which is realized in SYK, is actually N squared because I and J both go from 1 to N. So this is not a full rank SYK matrix, but what we call a low rank SYK matrix. So that's already the first example where so-called low rank SYK matrix emerges. So let's see whether there are other examples. Actually, there are other examples, and I will show two more examples more briefly. So another origin of this low-rank structure is it comes from this Yukawa boson-fermion coupling, and it was first noticed in this study that I cited below by Estelitz and Schmalian, motivated by Cooper pairing in strongly interacted materials. So what they considered is a model where you couple fermions to bosons. So in the first line, I I wrote their Hamiltonian, the interacting part of their Hamiltonian in a symmetrical way. So you have QNs, which are fermionic bilinears. They are coupled to some bosons. And now you can integrate out the bosons, and then you will get a forward interaction between fermions. But since the channel since when you integrate out the bosons, the rank of this tensor of this matrix Jij will be also given by the number of bosons. Now in realistic system, these bosons will be phonons, so their number will scale as the number of electrons. They will both be extensive. So you still have an extensive rank. Not so the rank is proportional to the number of fermions, not much higher than it as in SYK model. The second example. The third example is a cold atom example, and it came from an earlier work in our group, which I participated in. So this is also an experimental attempt to realize a SYK model in the lab. So what we try to do is we try to put atomic assemblies into a cavity mode, and so these atomic spins are coupled to a single optical cavity, and then one can show that the interaction between the spins mediated by the cavity optical mode is given by that kind of Hamiltonian. So you have SK and SLs are the atomic spins, so they are SU2, and then you see they interact in some Heisenberg fashion, but the interaction coefficients between the K spin and the L spin as a matrix, it factorizes. So instead of obtaining a full rank interaction matrix, you still have a low rank interaction matrix. Now, if you represent spins as fermion bilinears, you will get back something similar to a low rank SYK model that I wrote down earlier. So we have seen that this low rank SYK structure is actually everywhere, and it's more natural to realize it in the nature or in the lab than the full rank SYK model. So this motivated us to more systematically study these low rank SYK models, and this is what we did in this preprint, which is in the pipeline of PRB now. And it is done with Jae-Won, who is a PhD student, and Ehud, who is the PI leading our group. Okay. So let me restart by defining more systematically what we are going to look at. So I will write my Hamiltonian H as a sum of as a linear combination of square of fermion bilinears. So it's just another way of writing the fact that Jij is a low rank matrix. So I just rearrange the terms, and each Qn is a random fermion bilinear, and lambda n's are the coupling constants, and the number of the rank is R. Is the number of lambda n's on the fermion bilinears. So the good thing with large n is that basically whatever you write down is exactly solvable. So we can have a large amount of control over the models that we want to study. So here the rank is completely tunable, so I can make it scale with the system size in different ways. So R is some prefactor times the system size to some exponents, and the most interesting case that we will see is the so-called extensive rank, where R is proportional to n. And besides the rank, I can also tune the distribution of these coupling constants, and that will that we will see that will also play a role in the low energy physics. And in the end, what we assume to be featureless is these coupling constants U, I, J, N. So they are just some IID Gaussian random variables which we will normalize so that the Hamiltonian has a good thermodynamic limit. Okay, so that is the model. Any questions about the model? Okay, assume there's no. Yeah, so you see there are basically two knobs where you can tune this model. So now let me describe to you how these two knobs affect the physics. So the first thing, the first obvious thing that you can tune is the rank. So so let me first examine some simplest cases. If as we saw before, if the rank is n squared, the maximal, then you go back to usual SYK. That's the rightmost limit. And if the rank is 1, then actually your Hamiltonian is basically a free fermion Hamiltonian. You just need to square it. So that's basically non-interacting. So you see that as the rank increases, you go from non-interacting to very strongly interacting. So what happens in between? Actually, what we can show by solving this model in the larger limit is the following. So actually, as long as the rank is much larger than n, you recover the standard SYK. You don't need to go to n squared. And as long as the rank is much smaller than n, you recover the physics of rank 1. Basically, you get a free fermion solution at low temperature. So that leaves the only place of interest, the extensive rank regime. So as I indicated in this phase diagram, if you go to low temperature and if you are in extensive rank, you will find a new quantum critical and depend on the shape of the distribution. So that's the main message of the main new result of this of our work. So let me go into that more in more detail. So just to remind you that the Hamiltonian is written as a linear combination with these coefficients, and these coefficients can have a distribution when there are a lot of them. So if I assume that in the thermodynamic limits they have a distribution, I can start to classify this distribution. So it turns out that the following way is the good way to classify them. So the first thing you want to ask is that whether you have any positive lambdas, some ferromagnetic coupling. If not, then you are in class, what we call class 4. So if lambda max is negative or 0, then you're in class 4. And actually, as an example of class 4, we can cite the graphene flake example. Why is it in class 4? Because you have a Coulomb repulsive interaction. That's basically guarantees that you don't have any positive lambda. Now among the remainder of the distributions, actually we need to work more. So so the next class that we identify is characterized by the presence of a Dirac peak. So that's the class 3. So there, in class 3, there's a Dirac peak at the maximum value of lambda. So that will turn out to be important. And in class 1 and 2, you don't have a Dirac peak, and they are really differentiated by the rightmost singularity of this distribution. So if you have so class 1 is characterized by a edge that is vanishing, like in semicircle law, where in class 2 you have a divergent edge. So these are the 4 classes, and what we show is that these 4 classes give rise to different low temperature behavior. So in class 3, yeah. Is there a question?
No, just to, can you hear me?
Yeah.
Yeah, just to clarify, this rho lambda is an input of your model, right?
Yeah, rho lambda is the input. Very nice, yes. Okay. Rho lambda is the input. So I can choose whatever rho lambda and then I can solve it.
Okay.
Yeah. So here in class 3 and 4, my rho lambda is either all negative or it has a peak, a delta peak at its maximum, which is positive. So in these two classes, what we can show is that you realize a phase of matter which is really close to SYK, or actually its generalization, which is called the QSYK. So its Hamiltonian is really horrendous. It's written in the bottom of the slide. So instead of 4 fermions interacting, you have Q fermions interacting. And actually, there's a way to analytically continue Q to any real number, but that's clearly not physical in the context of QSYK described by that Hamiltonian. However, what we find is that our model, by tuning the rank divided by n, which is the O1 number, you can continuously tune Q basically. So what that means is that you can actually tune a scaling dimension, which is in the QSYK case given by Q, and you can tune the scaling dimension of the fermion continuously as a function of the rank. So it's basically plotted in the plot in the right of the slide. So the upper panel is class 3. So the scaling dimension goes from 0.5 to 0.25 as you increase the rank, and the class 4 is the bottom panel. So the scaling dimension goes from 0 to 0.25 as you increase the rank. And not coincidentally, the SYK4 scaling dimension is precisely 0.25. So it's the middle. So 2 delta equals to 0.5. So basically, you have all the scaling dimensions that you can wish for the fermion by tuning the rank. And moreover, with whatever rank and whatever scaling dimension, we can show that class 3 and 4 are both maximal scramblers. So I didn't show any of the calculation here, but we calculated the quantum Lyapunov exponent using exactly the method that is used for the Sachdev-Ye-Kitaev model, and we find the same results, that the Lyapunov exponent is maximal at low temperatures. That's a technical calculation, but I think the result is quite clear.
Question?
Yeah.
Yeah, sorry. So the scaling dimension, depending on the rank, will have consequences on the stability of this guy with respect to the two-body term?
Of the two-body term.
So you're going to discuss that or no?
Yeah, I will discuss that. Maybe I will discuss that by the end.
Okay.
The other classes. Okay.
Yes, go ahead.
Yeah. So now let me go to class 1 and 2. So they are very different. They are not maximal scramblers, and they are what we call the marginal Fermi-liquids. So they are characterized by the presence of quasi-particles, but whose decay rate is fast compared to Fermi-liquids. So in a Fermi-liquid, a quasi-particle of energy omega will have a decay rate proportional to omega squared. But in class 1 and 2, you have omega to the 1 plus eta, where eta is the exponent of the edge of the distribution. So if we consider eta smaller than 1, then you have a faster decay rate of low energy particles compared to Fermi liquid. So that has a few consequences. For instance, in class 2, we can show that the specific heat is not linear in temperature for low temperature, but it has actually a smaller power. So you have enormously large specific heat. Also, the quantum Lyapunov exponent is basically it's given by the quasi-particle decay rate. So it's temperature to the power of 1 plus eta in class 1 and proportional to temperature in class 2. So however, the bottom line is although they are not maximally chaotic, they are more chaotic than a Fermi liquid, and moreover you can basically completely you can interpolate between more chaotic to less chaotic by going from class 2 to class 1 by tuning the density of states near the maximum. So let me just recap. Yep, the question? Okay, so let me just recap and make a few remarks also regarding to the stability of two-body terms. So here are all our classes, and the class 4, as we saw, is a little bit special in that it has all lambda negative. But the general trend is that from class 1 to class 3, 4, you have more you go from weakly interacting to SYK-like. So let me first answer the question of stability with regard to two-body terms. So the answer is that class 3 and 4 are not stable with regard to two-body terms. So if you have two-body terms, the bond dimension will change. Sorry, not bond. Sorry, the scaling dimension will change to a Fermi liquid scaling dimension. However, class 1 and 2 are stable with regard to two-body perturbations. The reason for that is that they are already marginal Fermi liquids. So to go a step further, the reason why class 1 and 2 are such is that you have some condensation of the softest bosons in class 1 and 2. And so a condensed boson will generate a two-body term. So the two-body term is already dynamically generated, and if you have another weak two-body term, it won't ruin the phase. And so last remark. Why do you have a condensate and without gapping out? So usually it's very hard to get quantum criticality if you have a condensation transition. Then beyond the transition you still create a gap. So here what saves you is the so-called self-tuned criticality. So what happens is that when the softest boson condenses, you have also many bosons which have lambda just a little bit smaller than lambda max. So they are also very soft, and they will be critical. So you will have a continuous distribution of soft bosons, and they will keep you in the criticality without creating a gap. Okay. So that's okay. That's yeah.
One question is, so for this condensation, should I look at the behavior of rho lambda near the edge?
Yes. So the condensation will happen only for the boson with the largest lambda. So that's why this edge singularity behavior is so important for the low energy physics. So I think as an analogy, you can think about Bose-Einstein condensation. Okay, so if you have a very large density of states at low energy, then you will prevent condensation because you don't know where to go. That's what happens in class 3. The class 3 is basically like zero-dimensional both gas, and you won't condense. Now, class 2 is like a one-dimensional or marginally two-dimensional both gas, and you won't condense at the finite temperature, but you will condense at the 0 temperature. Class 1 will be like three-dimensional or higher both gas, and you will have a condensation of your lowest energy boson mode at finite temperature. Okay. Okay, so I think that ends the technical part of this talk, and in the rest of the talk, I want to go a bit further and discuss some ongoing and prospective applications of this work. So what we can do about with low rank SYK. So the first thing that we are doing is that we want to go beyond 0 + 1 dimension and construct a spatially extended system with the features that we mentioned. So this is ongoing work. So I'm just going to give you a taste with an example. So here what I'm doing is that I'm writing a more elaborate model where not only where I have many dots of fermions on a lattice. And each dot is like low rank SYK, but between different dots, the fermions can hop with some distribution relationship, and also I have some bosons which can also hop, and the third term is really like the Yukawa version of the low rank SYK model. So we look at, yeah. Okay. No. Okay. So we looked at this model, and we found that actually if the disorder is not transition invariant, so if the disorder is independent on each side, then this model basically reduces to low rank SYK of class 1 and class 2. What it means that the self energies are local, so they are diagonal in X spaces, and then the dynamical mean field theory reduces to 0 dimension, and you will get the same self-tuned criticality of boson. So this feature again, if the mass of the boson is low enough. So basically the 0 temperature phase diagram has two phases. You have a boring phase where the bosons are gapped out, and then you have and then if the bosons are light enough, you have a critical phase where you have soft bosons. So we are also looking at the transition invariance versions of such models, and we are trying to perform a systematic classification. So the motivation is basically that the boson can have really different physical meaning. It can be either phonon, or it can be some kind of order parameter of superconductivity. So that will govern, that will dictate how it couples to fermion. So there's some amount of work involved in this, and we also want to look at transport in such system, and we wonder whether we can find these strange metal behavior with T linear universal conductivity, and we are also interested in superconducting instability. So just to remind you that one of the studies that I quoted as a motivation to low rank SYK actually was motivated by Cooper pairing, and I haven't touched on that part in this talk. I always looked at the so-called normal state, but in these models, if you have spinful fermions, you can have superconducting states. So that's the condensed matter type application. So the second type of application that I have in mind is related to open quantum systems. So I'm very curious about this recent development on the dynamics of open quantum systems, or actually the dynamics of quantum information in open quantum systems, and this is attracting both high energy physicists and condensed matter and atomic molecular and optical physicists. So I just quoted the two very recent papers that represents, in my view, the two communities. So in the first paper, they try to study black hole information. They try to resolve black hole information paradox using open quantum systems. So they basically say the key to resolving it is actually some decoherence of the black hole radiation. And the second paper is on the so-called measurement induced phase transition. So it's an open quantum system, and there's a competition between unitary dynamics and continuous measurements. So continuous dephasing by the environment, and this can people have studied a lot and shown that this can induce a quantum dynamic phase transition. So all this motivated me to look at larger and solvable analogs of the so-called spin boson model, which was originally a model of quantum decoherence. So the idea is that instead of looking at open quantum system in the sense of Liouvillean Lindeblad dynamics, I can look at a closed system, but I really model the bath by unitary dynamics. So I couple my SYK to some bath of bosons, and look at its real-time dynamics using the same dynamical mean field theory. So this is ongoing work. I know how to do it. I know how this model behaves in equilibrium, and now the problem is that we want to look at real-time dynamics. So that's a future, this ongoing project. So maybe the last thing is also a bridge between high energy and condensed matter physics. So it's an application to the so-called wormhole teleportation. So what happens is the following. So from quantum gravity arguments, there's a proposal of sending information through a wormhole, which connects to space-times, and if you translate that into quantum mechanics, it becomes the circuit that I quoted in the left of this slide. So you prepare a thermal field double TFD, which is just an entangled pair of two identical systems, and if you trace out one system, then you will get a thermal state in the other system, and they will evolve under the same Hamiltonian but independently. So if you just do that, then you cannot send information from the left to the right. However, then what people do is that after sending some information using here a swap in the left bottom, after and involving some by some time, you apply some perturbation that acts on both systems, and that will actually open a window in the gravity calculation, so that the signal can just travel to the right, and then you can recover it in the right by another swap operation on the top right. So this has been proposed by high energy physicists, and there are some preliminary calculations. However, I think there are very few calculations but the intuition from gravity, from holography, is that in order for this protocol to work at a low temperature, the quantum system should be dual to some classical gravity. Now, otherwise, actually, the thermal field double will be basically disentangled, and you won't, and then you won't be able to do anything significant. So now what low rank SRK can do is that it can provide a interpolation of slow and fast scramblers. So since this kind of calculation can be done in large N models with some work, we can test how much scrambling is enough for this teleportation to work, and that's a probe of how much scrambling a quantum system must have to qualify for some gravity interpretation. So that's I think the most far-fetched application that I have in mind now. Okay, so I think that's all I wanted to say. So thank you for your attention, and yeah, if you have questions, don't hesitate. And also, if you have questions about my other projects, don't hesitate.
Okay, thank you very much. So you want to try to just maybe come back and if you have questions, maybe
yeah.
we can. Okay. Anyone has questions? Yeah, good. Can you hear me? I have a question about the beginning when you mentioned the graphene flakes.
Yeah.
If I understand correctly, so you have Coulomb interaction that you project into the lowest Landau level, but then it should be still relatively short-range in real space. It doesn't look so random to me. How does that
Yeah.
to
Yeah, good point. So actually the authors of this paper addressed that. So if you look at the slide that I show, so there's this panel B of the figure. So if you look at these LL0 bulk modes, they are actually very delocalized and random. So although the Coulomb interaction has some range, your wave functions are all delocalized. So you should think of fermions not as localized on physical sites, but as but each Ci is actually a creation or annihilation operator of a single particle mode, which is very delocalized. I guess then you won't have so local interaction.
Can you say again what's the color plot of
So the color plot, they are the single particle eigenstates in either the lowest Landau level, so that's the red ones, the first two rows, and then you have some edge modes. So we don't care about the edge modes. We care about these LL0 bulk modes. And what the authors claim is that they are essentially random. They are random and delocalized in the real space. Sorry, I cannot hear you very clearly. Can you speak maybe closer to the microphone, please?
So you said that you have the model 1 and 2 that have a condensation transition. So you have and then close to the softest mode, you have a pile of other very soft modes.
Yeah.
So does this come from, because maybe I've lost it, but does this come from a population? Which kind of population do you think that this? Can you give a bit of more details on that?
So I think this comes from this. I think this is best explained by just writing down the Schwinger-Dyson equations. So the boson mass is 0 for the softest mode, for the mode with lambda equal to lambda max. And so the effective boson mass is the bare mass minus lambda times something, some fermion loop. So if you look at the diagram, the diagram in below this slide, you see that the boson propagator, the boson self energy is basically given by a fermion loop, and this will lower the boson mass, and it has a coefficient lambda. So for lambda equal to the maximum value, the boson, this term will exactly cancel the bare boson mass, so that you have a condensation. Then for lambda close to lambda max, you have soft mode. Does that answer your question, or you want to ask something else? Okay.
I have one. So at the beginning, you started with some experimental platform for that. Can you somehow, or maybe you said, but so in your class, I think class 4, you said this graphene. Is it clear whether some of these? Is it clear whether some of these class that you discussed can be realized in those platforms, or?
Oh.
You know what I mean?
Yeah. So okay, that's a very good question. So what we show is that this graphene experiments cannot be the full rank SYK, and what is the most probable class is class 4.
Yes.
And now there's still a question whether it is really class 4, because if you want to go from graphene to class 4, you still need to assume that some matrix elements are featureless, and that remains to be checked.
Okay. And what about the cavity QED platform? Would that fit in which class?
Oh, that's nothing. That's a sub-extensive rank, so that's not chaotic. So that you cannot. It's not in class 1 to 4. That's really a finite rank. So it's really free. It's almost free.
I see.
And that's actually what we found in this study, but we didn't use the SYK machinery since it's not large N.
I see. And another question, maybe basic, but so you always consider density of states which are bounded. Is it somehow silly to consider tails, or it's just not well defined, or it's trivial, or what?
I think you will have a big trouble if you have tail going to plus infinity, because then the bosons in the tail will be too susceptible to condensation, and then I think our machinery will be in trouble.
Okay. I think I'm done with questions. Other questions? Yes, Grégoire?
Yeah, I have a basic question about quantum chaos, which I don't really know. So how can we define or measure all the absolute exponents? So you mentioned correlation, but
Yeah. So sorry, I haven't put in any equation on that. So okay, let me see how I can pull up an equation. Maybe let me go to our paper. It's easier. I didn't do this because we didn't invent it. It's kind of it's standard. So there's a very natural quantization of the classical butterfly effect, where you take. So let me first explain in words. So classical butterfly effect means that your configuration at the time t depends on configuration at time 0 in an exponential manner. So if you want to probe that using a Poisson bracket, you will write something like a qt Poisson bracket p0, which gives you del qt over del q0, and that's exponentially growing. So now what you do in quantum system is that you replace Poisson bracket by commutator. So you get some commutator, and that you want to measure how big is this commutator. So what you do is you take the square of this commutator. So then you will get terms. You will get a 4-point function if you do that. So if you imagine that each operator is a fermion, you get a 4-point function. And that 4-point function that you can calculate, and you can calculate how it depends on how it grows in time exponentially, and you can calculate it as exponents. And there's a quite mature machinery to do that for SYK type systems. So this is what I'm showing you. So I hope you can see that this is our paper. So yeah, so in all seriousness, this out of time correlate is defined like this. So it's really you insert 4 operators, but you go from time 0 to some large time t1 or t2, and you go back and go forth. So that's out of time, and this will grow exponentially. And to calculate how it grows exponentially, you need to deal with this so-called ladder kernel, whose diagram looks like figure 6. So you want to calculate. So these kernels are like linear operators, and you want to calculate their eigenvalues. And that will tell you what is the Lyapunov exponent. So here we did some serious calculation, and so the end result is something like 68. You do a lot of calculations, and you find these expressions for the eigenvalues of these kernels. And then what you do is that you plot these as a function of lambda. So here lambda is proportional to h in 68, and you plot them. You see that they are exactly 1 when lambda L is 2 pi times t, which is the maximal KO value. So this is a protocol to determine. So k equal. So if you intersect this curve with k equal to 1, that will give you the lambda the Lyapunov exponents, and here you get exactly that Lyapunov exponent is equal to 2 pi t, which is the maximal chaos. So that's a quite developed machinery, and we just applied it.
Sorry, related question. Is it clear? So you're saying that for this low rank, you can compute the auto in the same way as for the SYK, namely just the ladder?
Yeah.
Because it's still a large n.
Yes.
Still a large n.
Yes.